Okay, good afternoon again, everybody. I hope my internet is better now. Just let me know kung puputol-putol pa rin. But I don't know what to do after this. Naka-mobile data na uli ako. Pero anyway, I was telling you backstage that I still owe you a statement of the first problem set that I assigned to you in passing. And I think in our first meeting when we talk about LU factorization, remember we discussed the Doolittle factorization in details, and then I want you to write an exposition of Kraut factorization. So basically, siya naman yung LU factorization wherein you have ones in the diagonal of the upper triangular matrix. Okay, so you can mimic how I discussed Doolittle's factorization in the module I shared with you, or you can write it in your own style. So bigyan ko lang siguro kayo ng guide questions. And I'm also thinking of asking you to do an expose on what? On Cholesky factorization, all right? But I will probably, I promise, I'm gonna share with you I'll give you the statement, the formal statement of the problem set before the weekend. Para mapagplanuhan nyo during the reading break, mapag-isipan nyo during the reading break paano ko to gagawin. Ang deadline pa naman ay siguro sa dulo na ng SEM, ano? But once you finish the problem sets under me, sabihan nyo ako kagad, send me an email or a chat, and then I'll take a look at your portfolio para makita ko na at makapag-comment kagad ako. Because I guess we agreed that your final grade will be based on the final output. Pwede kami mag-comment while you're doing on your initial draft, and then you can edit your draft according to our comments or suggestions para yung final output na lang yung i-grade ko. Right? And then another thing is that aside from that, over the reading break, I'll start thinking about an application problem, which will show you how these methods that we're talking about in numerical linear algebra, or specifically in solving linear systems, is applicable to data science problems. Para makita niyo yung connection. Although the section is entitled Fundamental Methods in Data Science or Data Analysis. Kaya tinitingnan natin yung mga basic techniques that are probably running in the black boxes of data science algorithms. Gusto natin silang intindihin. Gusto ko pa rin ipakita sa inyo kung saan siya ina-apply or paano siya ina-apply, say, sa classification problems or sa clustering problems, all right? So you'll have a hands-on feel on how these methods are applied to data science problems. So yun yung gagawin ko over the reading break. And then once we come back from the reading break, I'll give you the problem set, which is basically kailangan yung mag-solve ng isang malaking system, and then to do it efficiently and accurately and with a certain stability, kailangan yung i-apply yung mga natutunan nating methods nitong mga huling sessions. So yun yung gagawin natin right after the reading break. But before going there, this week we'll talk about pseudo-inverses and regularization. So basically, natutunan natin from linear algebra kung paano mag-solve ng linear systems. If it's a big linear system, AX equals B, provided that that A is a square matrix and that it is invertible. Okay, then the solution to this linear system AX equals B is A inverse times B. But as I've noted last time, the computation of A inverse is not only computationally expensive, but it is also computationally unstable. Kaya usually ina-avoid sa mga algorithms yung pagko-compute ng A inverse, especially for large matrices. Kaya nga nagkaroon tayo ng LU factorization or Gaussian elimination techniques kasi nga masyadong unreliable at masyadong expensive yung pagko-compute ng A inverse. And then, but it's quite limited, although most matrices has an LU factorization, hindi rin siya ganun ka-stable. So tumingin pa tayo ng ibang factorization methods in the video recordings I shared to you last time. You saw QR factorization, wherein you factor matrix A into a product of a unitary matrix and another rectangular matrix R. And if you watch the rest of the video I shared with you, nakita nyo na yung QR factorization ay hindi lamang nag-work para sa mga square matrices. Because all matrices, kahit rectangular man yan, kahit square man yan, meron silang QR decomposition. And since it has a QR decomposition, madaling computean yung, or pwede siyang gamitin pagko-compute ng solutions ng isang linear system na rectangular yung coefficient matrix. But you see that QR factorization might be unstable. Pag ginamit niyo yung Gram-Schmidt process na classical, makikita nyo na, especially if you do it in a computer, masyadong malaki yung nagiging epekto ng round-off errors. Okay? Kaya kailangan natin yung modified Gram-Schmidt process, which basically reorders the operations involved. Equivalent yung dalawang processes in the sense that if you do everything by hand, you do everything completely exactly. All right? So wala kang round-off na ginagawa at every step, parehas yung magiging sagot mo. Pero once you ask computers to do the computations for you, magmamatter ng malaki. Kasi yung classical Gram-Schmidt process, siya ay napaka-sensitive niya with respect to round-off errors. Unlike the modified Gram-Schmidt process, na medyo rearrange mo lang yung operations, mas nami-mitigate yung epekto ng small rounding offs dun sa final computation. That's why the modified Gram-Schmidt process is preferable in getting a QR decomposition. But even in that particular case, malaki pa rin yung error na nakukuha natin mula dun sa QR factorization. Okay? If you have taken numerical analysis too, so you might have also encountered some iterative schemes on how to solve linear systems AX equals B. Siguro narinig nyo na yung Gauss-Jacobi, Gauss-Seidel, and then the successive over-relaxation method or the SOR method. So ito yung mga methods na pwede nyo gamitin. Pero now we'll be talking about an alternative na medyo, ito yung ginagamit ng mga computing softwares like MATLAB, right? So we'll start by talking about pseudo-inverses and then how they can be applied in solving linear systems. At ano yung advantage niya rather than using the inverse of a matrix, all right? Plus, titingnan natin in the latter part of the module, yun namang regularization processes. The regularization process is basically one way to mitigate sensitivity against small perturbations in your right-hand side vector. Okay. So I borrowed the modules I use for Math 175. So this is undergraduate material. So don't worry kung hindi kayo masyadong familiar dun sa concepts. Ano lang to, basic yung discussion. So what I'll do is to just go through this in a more diagonal fashion. Kasi parang sabi niyo ako lang yung detalyado masyado na nagtuturo. So maybe I'll try to mix it up today. So on the diagonal yung gagawin kong discussion. But let me know if you prefer to do it in a more detailed manner. All right? So kasi mas gusto ko talaga yung detalyado kesa dun sa dinaraanan lang yung mga concepts. All right. So pseudo-inverse. So unang problema, hindi lahat ng matrices ay may inverse. All right. So there's just a certain class, a small subset of the set of all square matrices ang nagkakaroon ng inverse. So what do we do whenever our linear system has a coefficient matrix that is not invertible? Or worse, hindi siya square at all. So hindi na mag-apply yung karamihan ng mga techniques na natutunan natin before. So that's why some mathematicians were prompted to develop sort of a generalization of the inverse. So ito yung pwede nating tingnan as a generalization of the inverse. It's a generalization because of two things. Number one, we want all matrices to have a pseudo-inverse. All right? Kasi napakaliit lang ng class ng mga matrices na may inverse. So pag magde-define ako ng generalized inverse, gusto ko itong i-generalize in the sense na lahat ng matrix ay magkakaroon ng pseudo-inverse. And number two, I just don't want to generalize the notion in that fashion, but I also want na kung siya invertible, yung inverse niya na yung pseudo-inverse niya. So ito yung dalawang properties ng generalized pseudo-inverse na titingnan natin. lahat ng matrices ay magkakaroon ng pseudo-inverse at kung invertible na siya, dapat yung inverse niya siya rin yung pseudo-inverse. There are several ways on how to define the pseudo-inverse of a matrix, pero yung pinaka-popular is due to independent work by the mathematicians Hastings Moore, Arne Bierhamar, and Roger Penrose. At yung tinatawag na Moore-Penrose pseudo-inverse. I don't know kung bakit natanggal sa billing nung pangalan si Bierhamar, alright? Pero ito yung tinatawag ng Moore-Penrose pseudo-inverse, and it would be helpful in solving linear systems. Ano? Now, what are the kind of linear systems that we are looking at? So basically, meron tayong dalawang klase ng rectangular systems na titingnan. Of course, meron kang mga square matrices na hindi invertible, pero ito yung mas general case. Una, meron tayong undetermined system. Of course, meron din mga overdetermined system, pero let's look at this linear system. So 1, 1, 1, 1, 1, 1, tapos meron kang vector x. Okay, so nadi-disconnect daw si Benpol. Or ako yung nadi-disconnect. Hindi ko sure. Okay ba or paputol-putol pa rin? Kasi okay naman ako. All right. Kasi naka 4 bars yung Wi-Fi ko. So I think I'm okay. So siguro Benpol sa ano yan? Sa Royal Cable pa rin. Kasi parehas tayo ng provider ano. So kaya nag-shift ako sa data. But kung paputol-putol pa rin, hopefully the recording will be better so you can come back later and watch the recording. Ano? Dun sa mga parts na napuputol-putol ako. So just some introductory examples. So tingnan natin itong undetermined system na to. The coefficient matrix is 2 by 3. So we don't expect this matrix to have an inverse kasi nga rectangular siya. So we're looking for a vector. This would be a 3 vector, right? So X would be 3 by 1 matrix, 3 rows, 1 column, right? Such that pag minultiply ko yung X1, X2, X3 dito sa matrix na to, we'll get 1, 0. But you will see that this doesn't have any solution, right? Kasi pag sinulat natin yung actual system represented by this by this matrix equation, magkakaroon tayo ng X1 plus X2 plus X3 equals 1, and X1 plus X2 plus X3 equals 0. So these are two non-intersecting lines in the 3D space. So ibig sabihin, or in the 4-dimensional space, so ibig sabihin, 3D space nga lang. So ibig sabihin ay wala tong solution. All right? And then the other guy, this one, actually this will have an infinitude of solutions. Infinitely many yung solutions netong system na to, all right? Because if you do the hand calculation, you will get the following solution, where x2 is any real number, all right? So ito yung dalawang klase ng undetermined system or rectangular systems in general. Merong infinitely many solutions at meron kang no solutions at all, all right? So we can use the concept of pseudo-inverse to characterize the solutions or the next best thing to a solution that we can get for these two types of linear systems. Ano? Kung siya ay no solution or meron siyang infinitely many solutions, pwede nating magamit yung konsepto ng pseudo-inverses para ma-characterize yung solutions o yung next best thing to a solution that we can get whenever there is no solution for the linear system. Okay? Now, on to the main event. Ano yung ibig sabihin ng pseudo-inverse? Sabi ni Moore, Penrose, as ni Bierhamar. Ito yung definition ng pseudo-inverse. Okay, and look at this. True to the promise of generalizing the concept of the inverse, yung definition na to will work for any m by n matrix with complex entries. Okay? So, kahit anong matrix yan, de-define na natin siya ng pseudo-inverse. Ano yung Moore-Penrose pseudo-inverse? Ito yung matrix A. Ito yung matrix A+. Okay? So ito yung notation natin para sa pseudo-inverse. Siya ay yung matrix na nakakasatisfy ng 4 na properties na ito. Okay? So just be careful when I write A+, this is the pseudo-inverse. in contrast to A transpose, which I write with a capital T. All right? So ito ay plus, hindi siya little t. So hindi to transpose, ito yung pseudo inverse. Okay? Now, what is A star or what happens when I star a matrix? Yung star ng matrix, siya naman yung conjugate transpose. Okay? Dahil complex yung ating matrix, para makuha si A star, kukunin mo muna yung transpose ni A, tapos i-conjugate mo siya. Alright? So yun yung ibig sabihin ng A conjugate transpose or A star. So for instance, if we have A to be the matrix I, 1, 0, 2 plus I, 3, and then say 2 minus 3i, alright? Yung conjugate transpose niya, kukunin ko muna yung A transpose. Ano? So ita-transpose ko si A, denoted by A transpose. So yung mga rows magiging columns at columns magiging rows. So this is gonna be I, 1, 0, 2 plus I, 3, and 2 minus 3i. Ito yung A transpose. But if we want the conjugate transpose, kukunin ko ngayon yung conjugate ng mga entries ng A transpose. So para makuha ko si A star, kailangan ko munang i-transpose yung matrix A, tapos kunin yung conjugate ng mga entries ni A transpose. So this is going to be negative I, 2 minus I, 1, 3, 0, 2 plus 3i. So this is A conjugate transpose or A star. Okay? Kapag ka real numbers lang yung entries ni matrix A, si A star ay kaparehas lang ni A transpose. Okay? Pero ginawa kong general yung discussion dito kaya I'm dealing with complex entries din. Okay. And then, ano yung sabi ni Moore Penrose at saka ni Bien Hamar, kapag ka meron kang matrix na complex yung entries, alright? Mukhang delayed yung aking medyo nagahang yung aking share screen. Pero anyway, hopefully you can still hear me well. Kapag ka meron kang isang complex matrix, ang A pseudo inverse or yung A+, tawagin kong A+ yung pseudo inverse. Si A+ ay yung matrix na nakakasatisfy ng apat na properties na to. Si A star yung tatawagin nating pseudo inverse ng matrix A. And it can be shown, but we will not write the proof, that any complex valued matrix ay merong unique na Moore Penrose pseudo inverse. So kahit ano pang matrix yan, lagi tayong may mahanap na one and only one matrix A+ that satisfies all these four properties. So that makes good to the promise na lahat ng mga matrices ay bibigyan natin ng pseudo inverse. Okay? However, definition 9.1 is not too much helpful in constructing the pseudo inverse kasi binigay niya lang yung characterization ng pseudo inverse pero hindi niya tayo tinuruan kung paano mag-compute ng pseudo inverse. In fact, the computation of pseudo inverse ay medyo what you call this? Medyo limited yung kaya nating i-construct by hand. Pero in theory, we know that there's a matrix A+ somewhere out there that can be treated as the Moore Penrose pseudo inverse of any matrix A, be it rectangular, be it square, be it invertible, be it not invertible. Okay? Yun yung sinasabi ng Theorem 9.1. And just a quick exercises, if you have nothing to do, nabobore ka, or habang nanonood kayo ng Netflix, pwede nyo itry itong exercises 9.1 up to 9.3 to verify being pseudo inverses, right? So, given ako ng matrix 1, 2, right? Obviously, hindi yan invertible kasi hindi nga siya square in the first place. So, what you can do is verify that if this is the matrix A+, then this matrix will satisfy all four conditions laid down in definition 9.1, making this matrix A+ to be the Moore Penrose pseudo inverse or just the pseudo inverse of the matrix A. Tapos ganin din yung sa exercise 9.2. Na tingnan nyo itong matrix A na to. Square siya, so may chance na maging invertible siya. Pero ang determinant niya ay 0 minus 0. So ang determinant ni A ay equal kay 0. We know that when the determinant is equal to 0, this matrix is not invertible. Right? Pero meron siyang pseudo-inverse. Ang kagandahan pa nito, itong matrix na to, pseudo-inverse niya yung sarili niya. Okay? And then in exercise 9.3, verify na ang pseudo-inverse ng matrix 1111 ay itong matrix na 0.25, 0.25, 0.25, 0.25. Okay? So basically, ito ay not invertible pa rin kasi ang kanyang determinant ay 1, minus 1, 0 pa rin, and yet now we have a concept of a pseudo-inverse. Okay? Now you can also try, think of an invertible matrix, your favorite invertible matrix. Tapos tingnan nyo na ang pseudo-inverse or kaya nyong i-verify na ang pseudo-inverse ng invertible matrix na yon ay yung inverse niya. Alright? So basically, here's what I'm saying. If A inverse exists, then the pseudo-inverse is equal to A inverse. Thus satisfying yung promise ko kanina ng dalawang properties ng pseudo-inverse. Okay? However, definition 9.1, as I mentioned earlier, is not constructive. Hindi niya tayo binigyan ng paraan para mag-compute ng pseudo-inverses. Sinabi niya lang ano yung properties ng pseudo-inverse. Now, I have a theorem here which gives us some ways on how to compute the pseudo-inverse for at least a specific class of matrices. Okay? Now, sabi ng theorem 9.2, okay, si A posibleng hindi siya invertible. Pero kung yung A conjugate transpose o yung A star times A ay invertible, then ang pseudo-inverse ni A is given by this guy. A star A inverse times A star. So yan yung definition natin ng pseudo-inverse. Or on the other hand, kung ito ay hindi invertible, baka naman yung AA conjugate transpose yung invertible. So kung si AA star naman yung invertible, ang pseudo-inverse naman ni A ay equal dito. So these are two ways on how to compute the pseudo-inverse. And surprising enough, mas computationally cheap yung pagko-compute ng pseudo-inverse kaysa sa pagko-compute ng inverse. Alright? Kaya halimbawa si MATLAB or Matrix Laboratory, which is a very powerful machine whenever you're working with matrices and vectors. Pag pinakompute mo sa kanya yung isang linear system, kahit anong linear system yan, by default, ang ginagamit niya ay pseudo-inverse. I think it's using this pseudo-inverse instead of the traditional inverse. Kasi nga, napakalaki ng problema kapag ka direktang inverse yung ginagamit nyo rather than using the pseudo-inverse. It has something to do with stability with respect to round-off errors. Okay? Okay, so now with theorem 9.2 in mind, you can go back to the exercises that we have laid down here. Baka kasi nagtataka kayo paano nakuha yung A star. So when you're reading the handout or the module from top to down, so mabe-verify nyo lang na ito talaga si A pseudo-inverse o si A plus by verifying the four conditions kanina. Pero ngayon, may iba na tayong paraan. Theorem 9.2 is telling us, kunin mo yung A star A, kunin mo yung inverse ng A star A, tapos i-multiply mo siya ng A star, makukuha mo si A pseudo-inverse. So you can apply theorem 9.2 as an alternative way to verify that if A is 1, 2, then A pseudo-inverse is 1/5, 2/5. Alright, so yun yung computational way at least ng pagko-compute ng pseudo-inverse kung invertible si A star A o kaya si A star. Okay, and then I still have a bunch of exercises here. So i-check nyo kung pwedeng gamitin yung theorem 9.2 para mahanap yung pseudo-inverse ng mga binigay ko na matrices dito. Okay? And I think these are some of these will be considered in the exercises or in the examples later. Okay. So any questions so far? Is the concept of the pseudo inverse making sense? Or sobrang putol-putol at choppy ako na you can't you can't get anything from the discussion? Or andyan pa ba kayo? Nagdi-Netflix na yata kayo, ang daya nyo. Ayan, walang nagre-react, so mas kinakabahan tuloy ako ngayon. Alright. Kasi wala nagre-react, hindi ko alam kung putol-putol ako. Pero full bars daw yung wifi ko eh, so I hope I'm still okay. Wala lang kayong questions, ano? Ito yung mga kinakabahan akong paano. Ito yung problema ko lang sa online classes. Because actually, gusto ko yung setup. Lalo na there are some classes that I think can be effectively taught even if you are in the online setup. Kaya lang nawawala yung facial expression. Lalo na ngayon na naka-off cam tayo. So, hindi ko alam yung silence nyo kung anong ibig sabihin. I always assume there are two possibilities whenever students are very quiet and they don't have any questions. Number one, napakagaling nung pagkakaturo ko to a point na wala silang makuhang tanong. Right? They understood everything. So I call that type 1 and that's what I prefer. Sana tahimik kayo, wala kayong questions kasi ang dali nung dinidiscuss natin. Pero meron yung kontrapelo, yung type 2, which is basically you're too quiet because you cannot formulate any sensible question because you don't understand anything I talk about. So hopefully type 1 tayo, hindi type 2. Pero just let me know if I have to repeat some parts para mas maintindihan natin yung lecture. Okay? So that's how you compute the pseudo inverse. Tapos tingnan natin ano yung relation, ano yung impact ng pagkakaroon ng pseudo inverse dun sa solution ng mga linear systems. So again, we consider the linear system AX equals B. Now, there are two possibilities that we have seen earlier. Be it A is singular, rectangular, invertible or not. So itong linear system na to, may dalawang posibilidad dyan. Una, wala kang solution. Pangalawa, meron kang solution. Kung meron kang solution, meron pang dalawang subcases. Number one, there is a unique solution vector X, or there are infinitely many solution vectors X. All right? Now, the beauty of the pseudo inverse is, kapag ka meron tong solution, then any solution can be written in this form. Sure tayo na kapag ka may solution, yung equation 9.2, it can be proven that any solution will be of the form equation 9.3. Basically, in-skip ko yung ibang linear algebra parts nito because tailored kasi itong lecture na to for undergrads. But if you want to talk about the theory behind this, so this will have, so dagdagan ko ng konting linear algebra, no? This will have a solution, okay, has a solution. If and only if, so ito yung characterization kung kailan nagkaka-solution itong AX equals B. If and only if the range of B is a subset of the range of A. Okay? So ibig sabihin kung yung column space o yung set of all linear combinations ng columns ni B, pero that will just be any multiple of B, ay subset ng column space o ng space na ini-span ng columns ni A, or basically the set of all linear combinations of the columns of A. Alright? So kung totoo itong inclusion na to, meron tayong solution dito sa AX equals B na to. Alright? And this result, itong sa row space, itong relation na to, has an equivalent statement in terms of the pseudo inverse. So if, the range of B is a subset of the range of A, if and only if si B ay equals hold on, A A transpose B. Hold on, kailangan ko itong isipin ng konti. Tama nga ba to? AX equals B, A transpose. Yeah, I think this is right. Okay. So that means AX equals B will have a solution if and only if B is equal to A times A pseudo inverse times B. Okay. So that's a characterization when we have a solution. So kapag ka itong system na to, be it a square or rectangular system, kapag ka si B ay equal lamang sa A pseudo inverse times B, then we will have solutions. And solutions will always be of this form. Okay? Sabi ng equation, sabi dito, lahat ng solutions, kung infinitely many solutions man yan, o meron lamang siyang unique solution, then kahit anong solution ay nasa form ng equation 9.3, where I is the identity matrix of the appropriate size. So si identity matrix I ay ka-size ng A transpose A for this difference to make sense. And W is any vector of the right dimension. Okay? So then, yes, lahat ng solution ay kayang isulat in this form. Well, you can try to prove it. One direction would be to show that vectors of this form is a solution to the linear system. Tapos yung pakabila, siguro yun yung mas komplikado, na kahit anong solution ay kayang maisulat in this manner. All right? Gawin ko yung isang part or sketch ko yung proof ng isang part na lahat ng vector na ganito yung itsura, solution siya sa AX equals B. All right? And then you can think of the other part. So siguro I'll I'll add a page and then we can sketch the proof there. Okay. Now here we want to show that any vector Z of the form this guy is a solution to AX equals B, right? Ito yung gusto nating ipakita, right? If such solution exists. Kung may solution, yung AX equals B, ang sinasabi natin lahat ng vector Z na ganito yung itsura ay solution ng AX equals B. Okay. All right. So it's easy. We just need to plug in Z into X, right? At ipakita na yung product ay equal kay B. So we just compute AZ. AZ will be A times A transpose B plus identity minus A, hindi pala A transpose, A plus times A times W. All right. And then we use the distributive property of matrix multiplication. We're going to have A inverse B plus A times identity minus A plus A times W. All right? So distributive property. Meron pa tong parenthesis dito. And then I'll use associativity of matrix multiplication. We'll have A plus times B plus I'll have A times quantity identity minus A plus A. Sila yung i-group ko, saka ko na siya ita-times ng W. Again, W is any vector of the appropriate size. Okay? Tapos, ito ay magiging A transpose B, but we have mentioned na merong solution yung AX equals B if and only if A pseudo inverse B is equal to B. So this guy will be B. All right. From a remark earlier. Yung sinabi natin na si AX equals B may solution if and only if B is equal to A pseudo inverse B. Tama ba yung pagkaka-remark ko? Yeah, there we go. Si B ay equal kay A pseudo inverse B. A pseudo inverse B ay equal kay B because ina-assume natin na merong solution. And then here we'll have plus, so I'll distribute the A inside the sum, and then again use associative property of matrix multiplication. I'll have A minus A pseudo inverse A times W. All right. But from one of the properties of the pseudo inverse, all right, balikan natin yung definition 9.1. So definition 9.1, ang sabi niya ay si A plus, ang bagal ng aking scroll, ayan. Property number 1, si A plus times A ay equal kay A lamang. Okay? Balik ako dun sa pinuprove ko na delayed pa rin pala. So, etong A plus times A ay equal lamang pala kay A. So basically, here we'll have B plus A minus A, W, by definition 9.1 property 1. Okay? And then this will just be the zero matrix, all right? Zero matrix times any vector W will just be the zero vector. The zero vector plus B is equal to B. Therefore, any vector of this form will be a solution to AX equals B. End of proof. Actually, hindi pa end of proof. What's left to be shown is lahat ng solution ay kaya kong isulat in this manner. Okay? Medyo mas komplikado yung proof, but you can think about it. But I'll illustrate this in one of the examples later. Tapos ayan na. Nagrereklamo na si Zoom, my internet daw is unstable. All right, hold on. Okay, now. So yun yung case, yun yung scenario kapag merong solution. Na i-relate na natin yung pagkakaroon ng solution ng isang linear system dun sa properties ng pseudo-inverse. Kung merong solution yung inyong linear system, laging kaya ko siyang isulat in the form equation 9.3 for some vector W. Okay? Now, paano naman kapag walang solution yung AX equals B? Now, what's the next best thing to a solution that we can get? Now, kapag walang solution yung AX equals B, tapos gusto pa rin natin na magkaroon ng notion ng sort of a near solution to the linear equation, ang tinatawag natin na near solution ay yung vector X star na makakapag-minimize ng residual. Alright? So we are looking for the vector X star that will make AX star very, very close to B with respect to some norm. Alright? So pwede nyo tingnan yung residual AX star minus B. Kukunin natin ano yung vector X na makakapag-minimize nung L2 residual na to, ng residual na to with respect to some norm. Alright? Kung merong solution yung ating linear system, so ibig sabihin yung X star, ito yung exact solution. And if you have an exact solution, AX star minus B will be the zero vector. Yung zero vector, ang L2 norm niya, kahit ano pang norm yan, ang norm ng zero vector ay 0, siya na yung minimizer. Alright? Pero kung walang exact solution, ang hanapin natin ay yung vector na may pinakamaliit na norm ng residual. So ito yung residual na tinatawag natin. This is the difference between AX star and the right-hand side vector. We want to minimize this norm. Okay? Pinakamaliit na size ng residual. Now, if you are taking the minimum norm solution with respect to the L2 norm o yung Euclidean norm ng mga vectors, ang solution na makukuha mo dapat ay yung galing sa pseudo-inverse. Right? And that's how the pseudo-inverse is very good. Hindi lang siya basta-basta sinolve, or hindi lang siya basta-basta ginagamit. May reason kung bakit ginagamit yung more Penrose pseudo-inverse kasi siya yung minimizer or siya yung makakapagbigay ng minimizer ng L2 norm ng residual. Right? So just a quick recall, kapag ka meron kang vector x, x1, x2 hanggang xn, alright, ang L2 norm niya ay equal sa square root ng sum ng squares. Alright? So, kaya yung solution na nakukuha using the Moore-Penrose pseudo-inverse is sometimes called the least square solution. Alright? So, kasi nga, siya yung solution na nanggagaling dun sa Moore-Penrose pseudo-inverse given by A plus times B. So, note how this looks like compared to the exact solution. Kung yung AX equals B, kung si A ay invertible, the exact solution is X equals A inverse B. Alright? Siya yung solution, dapat siya yung exact solution. Pero kapag ka walang solution yung ating linear system, palitan mo lamang si A inverse ng pseudo inverse. This will give you the least square solution. Because basically this vector x star will minimize the L2 norm of the residual. Siya yung may pinakamaliit na residual with respect to the L2 norm, which is just the square root of the sum of the squares of the entries in the error vector. All right? So I hope narinig niyo na yung least square solution, especially if you took regression, kung nakita nyo na to sa stats, so yung curve fitting or line fitting, regression line, etc., ginagamit mo yung least square solution. Kaya medyo gamit na gamit talaga itong Moore-Penrose pseudo-inverse. So aside from calling this as the least square solution, yung iba ang tawag dito ay yung normal solution. Bakit siya normal solution? Kasi ito yung solution na nanggagaling sa normal equation. So if you start with AX equals B, tapos si A inverse ay hindi nag-exist, o kaya naman mahirap computin si A inverse. Now, you can solve the normal equation instead. Right? So if you have a normal equation, you can just multiply both, to get the normal equation, you just need to multiply both sides of your equation by A conjugate transpose to the left. So mag-multiply ako ng A star sa left. Be careful, matrix multiplication is not commutative. I multiply the left-hand side to the left by A star. So dapat nasa kaliwa din yung A star ko din sa right-hand side. So dapat consistent. Now, I know that matrix multiplication is associative, so I don't care too much about the parentheses. Kasi basta yung order sunod-sunod, hindi nagma-matter kung sino yung i-group ko muna. Kasi associative naman ng matrix multiplication. And then, usually, A star A is invertible. Okay? So lalo na kung rectangular. Kasi halimbawa, si A ay say m by n, hindi siya square. Alright? So si A conjugate transpose ay n by m. So pagka kinuha mo yung product ng A star A, magkakaroon ka ng n by n matrix. So etong matrix na to ay n by n. There's a big chance that it is invertible. Alright? So kung siya ay invertible, I can multiply both sides by the inverse of such matrix. Okay. Okay, so nag-multiply lang ako both sides by the inverse of A star A, which I mentioned for some reasons, some nice reasons, usually nag-exist yung inverse niyan. Oh, by the way, before I forget, this is what we call the normal equation. Okay. So ito ay inverse nito, so that will just be the identity matrix. So we'll be left with X in the left-hand side. And then on the right-hand side, we're going to have A star A inverse times A star B. And this should look familiar, right? This is basically A pseudo inverse of B. All right? That's why we call the solution coming from the Moore-Penrose pseudo inverse also as the normal solution. Kasi siya yung nagiging solution ng normal equation. Okay? So this gives you an alternative kung paano magsosolve ng mga rectangular systems. And the nice thing about this is kahit anong matrix, meron siyang a pseudo-inverse. Alright? Rectangular yan, invertible yan, hindi yan invertible, square man yan. Lahat sila may a pseudo-inverse, so you can always compute for a pseudo-inverse times b. And you're guaranteed that that vector, this product, is basically the solution that will give us the minimum L2 norm of the residual. So basically, this matrix or this vector is the next best thing that you can get to a solution if there is no solution available. Now, if the system has a unique solution, then you're still good. Kasi yung pagkaka-generalize natin nung pseudo-inverse using the definition brought forth by Penrose, Bienhomar, and Penrose, ano? So kapag kasi A ay invertible, yung A star ay equal kay A inverse. So basically what we get here is X equals A inverse B. And this is the exact solution. And this would be the only solution because this will minimize the L2 norm. Dito nagiging 0 yung L2 norm ng residual. Okay? And this is what I'm telling you kanina na kahit yung ibang mga programming languages like MATLAB, ano, so hindi nila kino-compute yung A inverse kasi medyo mahal yung pagko-compute ng A inverse. So pseudo-inverse yung kino-compute. Well, why is that more practical than computing the inverse of the matrix A? Kasi imagine, usually sa data science or sa kahit anong inverse problem, usually ang meron tayo ay isang tall matrix. Tall matrix, ibig sabihin yung number of rows ay mas malaki usually sa number of columns. Okay? So meron kang matangkad na payat na matrix, all right? Because in linear systems like this, every row will correspond to a data point. So usually, ito ay nanggagaling sa mga measurements. So bawat row ng isang rectangular matrix na sinosolve sa inverse problems o sa data science ay nanggagaling sa readings from actual data or actual measurements. While the columns, all right, yung columns naman ito, siya yung nagko-correspond dun sa number of unknown parameters, right? Kasi yung number of columns, siya yung mamumultiply neto. So parang mali yung drawing ko. Dapat pala ito ay mas maliit ng konti. So usually, we want an overdetermined system because we want to accommodate as much data as possible coming from physical readings or physical measurements. Kasi bawat isang row ay isang data na name-measure natin. And I want to get as much or as many sample kasi central limit theorem from stat yung ginagamit ko rito. The more data, the better. Alright? Pero gusto ko konti lang yung parameters, konti lang yung degrees of freedom because you can think of the unknowns to be the characterizing properties or the parameters characterizing the phenomenon being observed. So gusto mo konti lamang yung unknowns. So basically, marami kang rows, marami kang columns. Now, if you compute for the pseudo-inverse, ang titingnan mo lagi, kung ito si matrix A, ang titingnan natin ay si A conjugate transpose A. Tapos i-invert ko yan, tapos A star B. Ito yung ating solution galing sa pseudo-inverse, right? So, kung si A ay M by N, na si M ay super mas malaki kesa kay N. So, ibig sabihin, yung conjugate transpose niya will be N by M. So, therefore, A star times A will be N by N, a much smaller matrix than what I would have obtained if I considered A star. Kasi maging M by M naman yon. Kaya, mas maliit yung matrix na A star A, mas madali siya theoretically hanapan ng inverse kesa dun sa A star A. Or basically, kesa gawin ko tong square matrix na medyo mas malaki yung number of rows. Yeah, na magiging malaki yung number of columns din. Kasi kailangan kong gawing M equals N. So basically, mas lumiliit yung dimensions ng inversion kapag ka ginagamit yung pseudo-inverse. Alright? So let's look at some examples over here. So example 9.1, gusto kong isolve itong system na to. Now, the vector B, the vector 2461 is not in the range of A. Ibig sabihin si 2461 ay hindi linear combination ng mga columns ni A. So ibig sabihin walang solution yung AX equals B. So the question is, what's the next best thing to a solution that we can get? Now, if you took some time, extra time to watch the recording I shared with you last time, may iba't ibang paraan para ma-compute or makahanap ng solution dito. Pwede niyong gamitin yung householder QR decomposition for the matrix A to get an approximate solution or a near solution to AX equals B. So pag ginawa niyo yon, ito yung makukuha niyong solution mula dun sa householder QR decomposition. Kasi sabi ko nga yung QR decomposition, nag-work siya kahit rectangular yung matrix. Okay? O yung coefficient matrix. Pag ginawa niyo yung householder approximation or yung householder QR decomposition, you can find the following solution or the following near solution to AX equals B. Pero gaano kaganda itong solution na to? Well, hindi siya ganun kaganda. Kasi pag kinuha ko yung AX times this vector, ito yung makukuha ko, 3, 3, 3.5, 3.5. Pero ano yung right-hand side natin? 2461. Napakalayo. Alright? Now, to quantify how malayo is malayo, yung sinasabi kong malayo rito, kukomputing ko yung relative error. Okay? So, kukomputing ko yung L2 norm ng residual. I want this to be as close to 0 as possible. But to give me a more insight, about how good the approximation was, i-divide ko to by the norm of the right-hand side na minamatch ko. Para alam ko kung ilang percent yung error. Okay? So, makukuha ko yung size ng residual, kukunin ko lang this vector minus this vector, kukunin ko yung L2 norm para makita ko ano yung size ng residual. Pero kung size lang ng residual yung titingnan ko, hindi ko alam kung malaki na ba yun or maliit ba yun with respect to the size of the right-hand side. That's why I always rely on the relative error. So I'll take the residual, I divide it by the size or the L2 norm of what I want to get theoretically. Now I get 0.5044. That means pag ginamit ko yung householder QR factorization, 50% yung error. At hindi siya ganun kaganda. Right? Hindi ganun kaganda yung fit. Now, could I make this or can I find a better approximate solution or a better near solution to the problem AX equals B? We know that we cannot get an exact solution kasi nga wala naman dun sa range ni A si B, pero ano yung pinakamalapit na pwede tayong magkaroon to a solution? Now, I can use the Pseudoinverse, and I have in the module the step-by-step, almost step-by-step, ano? So, given si coefficient matrix A, kunin nyo lang yung conjugate transpose niya, pero tapos ipag-multiply mo sila, ito yung makukuha mo, tapos i-invert mo itong matrix na to, you will get this guy, and then compute a pseudo-inverse, you will get this guy, all right? And then multiply this to B, you will get the vector X. So the solution that we get from the pseudo-inverse is negative 6.375, 2.75, and 0.125. Okay? Pero how good this is? How good is this? Well, number one, theoretically, we are guaranteed that this solution will give us the minimum L2 norm. So yung residual o yung relative error na manggagaling dito sa solution X star will be smaller or is guaranteed to be smaller than the L2 relative error that we obtained from the householder solution X sub H. And true enough, pag kinompute ko yung L2 residual o yung relative L2 error, 0.4636. Hindi pa rin siya ganun kaganda. Alright? Because the error is still 46%. Pero ang kagandahan nito, theory suggests na ito na yung pinakamaganda. So ibig sabihin, etong parameters na to, ito na yung magbibigay sa atin ng pinakamagandang fit dun sa ating data with respect to the L2 norm or to the least squares error. So kung sa regression line ito, etong parameters na to, yan yung parameters ng line na magbibigay sa atin ng may pinakamagandang fit dun sa ating data na 2461. Okay? Na 2461. And we cannot get any better than that. Kahit pagbali-baligtarin mo pa man yung mundo, wala nang mas magandang solution kaysa dun sa binigay sa atin ng Penrose Pseudoinverse. All right. Now, if you're using MATLAB, may prescribe ba si Sir Joms na programming language? Kasi ako mas MATLAB yung ginagamit ko. So I can share with you some MATLAB codes that I'm using. Anyway, free naman yung MATLAB. If you have your UP email, you can just go to the website of MATLAB. So search nyo lang MATLAB download. So dadalhin niya kayo sa mathworks.com. Mathworks is the company that makes MATLAB. And I highly suggest MATLAB for matrix calculations kasi designed talaga siya for vectors and matrices. So yeah. Ang ibig sabihin nga ng MATLAB ay Matrix Laboratory. All right. So just go to their website and then create an account using your UP email. Tapos kapag nakagawa ka na ng account, pwede mo nang i-download yung buong package ng MATLAB. And I encourage you to take advantage of that subscription kasi hindi mura yung subscription kay MATLAB. Kasi during my studies, MATLAB lahat ng codes na sinulat ko para dun sa research. Tapos nung pabalik na ako ng Pilipinas, hindi ko pa alam nun kung merong subscription ang university sa MATLAB or wala. Alright? Nag-isip na ako, nag-ipon na talaga ako ng pambili ng license ng MATLAB. I think ang license ng MATLAB ay yung basic. $500 a year. Tapos for every package or toolbox na ida-download mo, additional $500. Ay hindi, pagka-academic license yata, $500 per lifetime na yon. So, ang dami kong package na kailangan. Kailangan ko yung optimization package, kailangan ko yung symbolic toolbox, kailangan ko yung signal processing toolbox, and so on. So, kailangan ko, siguro, nung nagpa-quote ako, kailangan ko ng mga $5,000, ano? And then luckily, may post si UPLB na meron na pala tayong subscription sa MATLAB. So ang laki nung natipid ko kasi hindi ko na kailangan bumili ng subscription. So I highly suggest you take advantage of it. Now, kung kay MATLAB, so itatype mo lang yung AX equals B. Probably we can devote a session for me to introduce you to MATLAB probably after the reading break para magawa niyo yung problem set na ibibigay ko. So kay MATLAB, pag nasulat mo na si matrix A at saka si right-hand side vector B, ang pagko-compute ng solution using the pseudo-inverse ay either x equals Pinv, or Pinv stands for the pseudo-inverse, Pinv of A times B. Ito lang yung syntax para makuha yung solution B. So, ang dami nating pinagdaanan. Tinuruan ko kayo kung paano computein yung pseudo-inverse A+. Na siya si A conjugate A, tapos i-invert mo, tapos ito times mo sa A star. Pero kay MATLAB, isang command lang yan, P-inverse. Alright? Or if you're solving a linear system, pwede naman ganito lang. A\B. Ito na yung ibibigay niya sa inyo yung solution vector. Yung least square solutions which is obtained by taking the Penrose pseudo-inverse. Okay? So maybe more on that later or probably next meeting. So tingnan natin. Some more example. Okay, so in example 9.2, pinapahanap yung least square solution ng AX equals B, where again we have a rectangular coefficient matrix. This is a 3x2 matrix, and we have a 3x1 output. So ito yung sinasabi ko. Gusto nyo halimbawa mag-fit ng humanap ng parameters na makakapag-describe dito sa data na to. Meron kang tatlong data readings, 0.25, 0.26, and 3.32. Tapos alam mo na yung governing principle dun sa phenomenon na ino-observe mo, ay kaya mong isulat in terms of this matrix. Alam mo, meron lang dalawang parameters na nakakakontrol doon sa phenomenon. So meron kang dalawang parameters na hinahanap, x1 and x2. So you will solve for the parameters x1 and x2 that will fit this data the best. Alright, dalawa lang yung unknown parameters na nag-describe doon sa phenomenon. Now, kung nagbago yung isip mo, kulang yung 3 samples. Pwede ka dito magdagdag ng mga samples. Pwede ka pa magdagdag, halimbawa ng 7 samples. So you'll have 7 data readings, and then you can compute 7 more rows in your coefficient matrix. But nevertheless, you will still have a very tall but thin coefficient matrix. Isa pa rin siyang overdetermined system, which is actually representative of what really is happening in practice, either data science or inverse problems. Ano? So para doon, pseudo-inverse pa rin yung pwede niyong gamitin para ma-solve yung, yung problem. Ano? So if you're doing it by hand, so you can first compute for A conjugate transpose times A. Dahil puro real lang naman yung entries ni A, so A conjugate transpose is the same as A transpose. So you have here a 3 by 2 matrix. A conjugate will be 2 by 3. So this guy would be 2 by 2. Madaling i-check kung siya ay invertible. Tapos invertible siya, so madali siyang kunan ng inverse. Mako-compute nyo ito. Tapos i-multiply nyo si A star by B, you will get 1, 1. And then, now, gaano kaganda yung solution na nakuha natin kay 1, 1? Well, actually, if you multiply the matrix A with the least square solutions that we got via the Moore-Penrose pseudo-inverse, so kunin mo yung A times X star, makukuha mo eksakto si B. So, ibig sabihin, alright, meron tayong nahanap na solution. Alright, ang solution natin ay, exact solution natin ay si 1, 1. Now, question, will this be a unique solution, or are there some other vectors X star that will give us a solution? All right, or actually which acts as a solution to the linear system that we have. Well, pwede natin gamitin yung result natin kanina. Meron tayong remark kanina na kapag ang isang linear system AX equals B ay solvable, then any solution will be of the form, ano nga yung form? Sorry, I have the memory of a goldfish, so hindi ko to tanda. Kailangan kong balikan yung notes ko rito sa taas. Sinabi natin, ayon, lahat ng solutions sa isang linear system will always be of this form. So copyin ko siya sa baba. Gusto ko lang kasing i-illustrate na wala na tayong ibang solution na mahanap. So sabi nung theory natin kanina, lahat ng solution, ganito yung magiging itsura. Alright? Now, for any vector W. Pero ngayon, pag kinompute niyo yung A pseudo-inverse times A, in the case of our matrix A here, pag kinompute nyo yung A pseudo-inverse times A, this will be the identity matrix actually. All right? So this will be a zero vector or a zero matrix. Zero matrix times an arbitrary vector will still be the zero vector. So we will be left with a unique solution A star or A plus B. So meron kang unique solution pa rin. Pero kung nagkataon na yung A pseudo-inverse times A ay hindi naging identity, then makakakuha tayo ng infinitely many solutions. Magbigay ka lamang ng arbitrary vector W, you multiply it to this guy, you add it to the prior solution that we got, kasi ito yung isang particular solution na nakuha natin, mag-add ka lang nito, solution pa rin yung makukuha mo. So parang ano siya, superposition ng solutions ng linear system. Meron kang isang solution, if there are other solutions, then you can obtain it by adding this vector to the least square solution. Right? Pero in this particular example, this guy happened to be the identity matrix, so wala na tayong ibang solution na mahanap. So there would be a unique solution, and we found that. That will be the vector 1, 1. Okay? And then probably, my parting example for today's meeting ay example 9.3, ano? Ito yung example ko kanina na merong infinitely many solutions. So here you have a 2 by 3 coefficient matrix. So we're looking for a 3 by 1 solution vector X na magbibigay sa atin ng 1, 3. Nakita na natin kanina or dun sa explanation ko kanina, pag if you're patient enough, ano? So if you write X to be X1, X2, tapos mag-Gaussian elimination ka, makikita mo na any solution will be of this form, where X2 is an unknown parameter or it's an arbitrary parameter. So meron tong infinitely many solution. Tapos tingnan natin, kaya ko ba itong makuha using the promise of the Moore-Penrose pseudo-inverse? Okay? So let's do it step by step. So simula ka uli kay A. Ngayon, gusto mong computein ano yung pseudo-inverse. Para mahanap yung pseudo-inverse, tingnan mo muna kung invertible yung A star A. Unfortunately, when you do A star A, you will get this matrix as your product, right? And obviously, this is not invertible because naulit yung yung isang row, all right? Since one row is equal to another row, the determinant will be 0, therefore this is not invertible. So hindi nyo magagamit yung unang option dun sa theorem 9.2. Pero on the other hand, if you try AA star, makukuha mo ay 2 by 2 naman, 3, 4, 4, 6. Determinant is 18 minus 16 equal to 2. So ibig sabihin ito ay invertible. So pwede nyo gamitin yung other half ng theorem 9.2. Ang inverse niya ay ito. Tapos, by theorem 9.2, ang pseudo-inverse ay equal dito. And then if you do the computations, the pseudo-inverse can be found to be this matrix. And then that means the least square solution will be this guy. Negative 1/2, negative 1/2, comma 2. And then you check. This solution is an exact solution. Kasi yung AX star ay eksaktong equal kay B. So meaning, meron tayong solution, so there's a possibility of having infinitely many solutions. But we know that. Bine-verify lang natin na infinitely many talaga yung solutions. Now, eksakto to. So ano pa yung itsura ng ibang solutions? Well, gagamitin ko lang yung remark natin kanina na lahat ng solutions dun sa linear system ay ganito yung itsura. Alright? Where a pseudo-inverse B na compute na natin to be this guy. So, ito yung isang particular solution. Alright? Magdagdag lang daw tayo sa kanya ng vector na to where W is any vector. Alright? So, makakuha pa tayo ng isa pang solution. So, what I'll do here is I write W as W1, W2, W3. I'll copy over our particular solution. I'll just expand this guy. I'll get this. I'll simplify. I'll do the matrix computations. I will get this. Tapos, i-multiply ko lang itong dalawa. I'm gonna get this. And finally, yung arbitrary solution ko or yung class of solutions ay ganito yung magiging itsura. Okay? But if I will let this guy to be equal to x2, kung ito ay tatawagin kong x2, then it's easy to show that this guy will be negative 1 minus x2. Alright? So therefore, itong equation 9.7 can be written as negative 1 minus x2, x2 comma 2, which we already know from above. Na ito yung infinitely many solutions. Okay? So I think I can end here. In summary, ginawa natin ngayon, generalize natin yung konsepto ng inverse. Kasi hindi lahat ng linear equation, hindi lahat ng matrices ay may inverse. So we generalize it in the sense of, number one, lahat ng matrices ay dapat magkakaroon ng pseudo-inverse. And second, ang pseudo-inverse ng isang invertible matrix ay yung inverse niya. And if we will use or if we adopt the definition brought forth by Moore, Penrose, and Bienhamar, nakita natin na yung nakukuha nating solution by just replacing A inverse by A pseudo-inverse. The solution X equals A pseudo-inverse times B is actually the least square solution to the equation AX equals B. And not just that. If we have an exact solution, then we can use that exact solution to find the family of solutions to our linear system. Kung meron siyang infinitely many solutions. Okay? So it seems that we are getting into a more perfect theory of linear equations na, okay, ito yung butas sa 120. Hindi lahat ng equations ay merong unique solution. So kung wala siyang unique solution, basically it can be due to the fact that A is non-invertible or A is not square, na solusyonan na natin yon sa paggamit ng pseudo-inverse. Wala nang butas doon. Kaya lang, from a numerical standpoint, meron pa palang problema. Kasi na-address natin yung existence of a solution or a non-solution or a near solution, pero yung machine implementation nito ay magkakaroon tayo ng konting problema. Because you will see in data science, yung right-hand side ng ating linear system ay nanggagaling sa physical measurements. And we do not have a perfect way to measure things. Kahit anong paraan ng pag-measure, laging may measurement error. So, we want our solutions to take into account yung error o yung noise dun sa data na ginagamit natin dun sa linear system. Kasi kapag tainted by noise yung data mo, makaka-apekto yon dun sa solution na makukuha mo dun sa linear system. So basically, kapag highly sensitive yung linear system mo to perturbations in the right-hand side, meaning a very small noise or a very small measurement error in the data collection process, malaki yung nagiging epekto niya dun sa parameter extraction. Because the solution that you can get from the system AX equals tainted data would be very much different from the solution that you get if you're solving AX equals B, where B is the perfect data. So paano natin ma-mitigate yung epekto na perturbation dun sa right-hand side, which could be due to measurement error, data noise, or basically round-off errors in computer? Gagamit tayo ng regularization techniques. And I hope to cover two types of regularization techniques, yung tinatawag na L-curve technique, which is very popular in the engineering literature. Ito yung madalas nilang ginagamit kasi simpleng-simple to. Pero tayong mga mathematician, ayaw natin ng L-curve, gusto natin, pabida kasi tayo. So ginagamit natin na yung Tikhonov regularization, which is basically an optimization problem, which we will see later, right? And may isa pa, yung singular value decomposition na I'm thinking of discussing probably in one of the future meetings. All right? So I think that's it for today. We can call it a day, unless you have some questions. Okay, mukhang walang questions. Hopefully, naitawid yung internet connection ko today. All right. So, yeah. So we'll continue discussing this. So by the way, I already have a copy of this module dun sa website natin. So ito yata yung number 3 dun sa learning materials. So you can download it. Sino ba sa inyo yung nag-Math 175? Si Mitch lang yata yung nag-175, no? 175 is a numerical analysis course in UPLB. And usually, tinuturo ko to dun sa 175, but I assume na hindi kayo lahat ay nag-175, kaya nire-recycle ko na lang yung material ko galing doon. Kasi importante ito. Alright? And then, ito yung mga announcements ko kanina. I'll give you the detailed instructions for the first problem set, which is basically an exposition of Kraut factorization and Cholesky factorization one of these days before we go to the reading break. And then over the reading break, I'll design a sort of parang lab exercise in the form of a problem set wherein you can apply the things that we learned in the past few sessions applied to a actual data science problem. Just a simple data science problem. Hindi ko naman masyadong papahirapan. So basic lang, para makita nyo ano yung implication o saan ginagamit itong mga napaka-fundamental techniques sa pagsasolve ng linear systems sa isang applied data science problem. So makita natin to next time, and probably you will be playing around some programming exercises kasi malaki yung matrix na ibibigay ko sa inyo para mukha talaga siyang data science, ano. So pwede niyong balikan over the reading break kung nagtatrabaho kayo during the reading break, ano, pag-isipan niyo na anong programming language yung gagamitin ko. Kung gusto niyo mag-MATLAB, kasi MATLAB yung may mga codes na ako para dito, so na pwede kong i-share sa inyo. So pwede nyo nang simulang pag-aralan si MATLAB. Alright? But again, I will not prescribe a certain programming language for you guys. So kasi ano lang naman yan, semantics lang yan, syntax lang yan. So kayang-kaya nyong i-translate one syntax to the other. Okay? So let's call it a day here. If you don't have any questions, thank you guys for joining me today. Enjoy your dinner, your night, and let's see each other again on Friday. All right? Bye everyone.
Thank you po. Thank you po, sir.
Thank you, sir.
Alright.